presentation will be very much giving an overview of where we are with practical implementation of brine mining. It is happening slowly, but there are a number of projects that you may have heard of, and I'll mention also a few projects that are in the works, and what is new and different in those projects from what you may know or have seen in other presentations. What is brine valorization? That's basically harvesting of valuable minerals from the brine. Often people refer to it as zero liquid discharge, but those are two different things. Zero liquid discharge is a side effect of brine valorization, and when we start looking at it in NEOM, trying to get to zero liquid discharge as a prime goal, we found that that's not necessarily very cost effective because of the looking at it, and as many do, of removing brine as a waste product, as a mixed brine, which has no commercial value. That's why we have to reconsider and look into other options where we could actually valorize minerals that can be produced and sold at competitive pricing compared to what we have on the markets today. Next is, I'd like to talk about, which is part of the brine valorization, is producing green chemicals from the brine. At this point, in NEOM and other locations, there is a significant amount of work trying to figure out how can we produce every single chemical we use in full-scale desalination plants from brine. And now we know, and we've been doing that for a while, and I'll explain briefly what is it that we do to be able to get basically to what we would refer to as circular economy, where we don't have to buy any chemicals anymore. We could actually extract everything we need from the brine itself. That is a significant step forward, and it will continue developing as time passes. And then another point that I would like to discuss is the use of brine for various non-chemical industry products, like for example, producing concrete. That is becoming very popular, and in Saudi Arabia it's now widely used for restoration of corals in the Red Sea. It is very surprising to see, but logical, that if you put one piece of concrete that is made out of typical concrete constituents, and one that is actually made with brine that contains a lot of calcium and magnesium, the shellfish and the coral does know which one is which, and they prefer and populates much faster the one made from brine. So that is an interesting fact and observation which caused brine products to be of significant benefit. We in NEOM have sold over $10 million worth of actually this type of brine restoration process. So it is very much possible. As you've seen this figure before, in desalinated water, 86% of the salts are sodium chloride. Sodium chloride is considered of low value if it is of low purity. However, we have developed technologies in the industry today that allow us to get to purities of 99.6%. Purity that we get from a common solar ponds are about 96%. That mineral is not necessarily very suitable or valuable for the chlor-alkali and other chemical industries. It's much, much more valuable to go to 99.6% purity. Just to give you an example, the cost of 96% purity, that's brine obtained through solar evaporation, it's about $25 a ton. 99.6% purity of the same sodium chloride is $75 a ton. In some countries, like Indonesia, it's $120 a ton. So actually producing high purity products significantly improves the possibility for us to have a revenue. Besides the sodium chloride, the next in line, as to say, as far as substance, is magnesium, potassium, and calcium. Those are the key minerals that get us to approximately from 86% to about 92-94% of all minerals. The rest of it is small micro minerals, which however could have very, very high value for the future of the industry. And as was mentioned by Dr. Sean, we actually been working with them on developing rubidium selective membranes and rubidium selective resins, and why is rubidium so interesting? for us is because what you don't know yet, but hopefully you'll hear soon, is the next fuel for production of energy is actually rubidium chloride. There are reactors that have been developed. They're not yet publicly available, but they will become soon, which run on rubidium chloride, and they're extremely efficient. Produce directly electricity. There is no nuclear process involved. So rubidium may become the future of power. This graph shows a very important fact, and that is if we compare what we have today as terrestrial sources of minerals that we normally would achieve by having terrestrial mines, surface mines, and we compare the same minerals to what's in seawater, you will see many orders of magnitude higher amounts of all key minerals in seawater than the same minerals in known and available terrestrial mines. What that tells us is that ocean could become and will become the next main source of minerals worldwide. Because of the terrestrial mining involves significant environmental pollution, and also it becomes more and more complex. The mines that we're using are more difficult to get to. The price of production of the same minerals from brine is becoming very, very competitive. This figure shows basically that not every mineral today, with the existing technologies we know and have, would be cost effective to compete against what is available in the market through terrestrial mining. The line, all the black spots are indicating minerals that we don't have yet technologies to develop. So for you as researchers and scientists, it's a great opportunity to develop those technologies that are below the dotted line, the black dots. They indicate how many valuable minerals we have, which we need to get to the point where we could produce them competitively. The minerals above the line are all minerals that we do have technologies for today. They do exist, and some of them are used in practical applications to actually mine them at more competitive prices than what we would do from terrestrial mining. And as you would notice, sodium chloride, potassium, magnesium, and calcium are on the top of those. You would see also rubidium in that. We can also mine uranium, iodine, bromate. So those are valuable minerals that can be, at this time, extracted at lower prices. Where do we start? It makes sense to start with sodium chloride because 86% of seawater salt is sodium chloride on one end. On the other end, it's a fairly expensive mineral, and there is a huge demand for it. Majority of that demand is in the Middle East, but also in the US, China. And what is it that sodium chloride is used for, besides the normal uses that we know? It's used mainly in the chlor-alkali industry, and in the Middle East it's used because it is an attractive way of making liquid PVC. Liquid PVC is made of two substances, sodium chloride and oil. If you have both, you certainly can produce liquid PVC. Then liquid PVC, by adding various additives to it, can be converted into any plastic that we know and use today. So that really opens up a big market and industry. And what is interesting in this calculations is I wanted to show you 100,000 cubic meters a day desalination plant, which nowadays would be considered medium size. It used to be big size, but nowadays big size plants are 1 million cubic meters a day and more. So if we take 100,000 cubic meters a day plant, we can produce out of it about 1 to 1.2 million tons of salts per year. If we look at the annual revenue, if we are selling that water that we produce at the plant at 60 cents per cubic meter, which is a reasonable pricing nowadays, we will be getting revenue of $22 million per year. If we look at the sodium chloride sale as extracted currently through available technologies, we could sell it for $65 to $75 per ton. So the revenue, as you notice the two numbers, the revenue from water is significantly smaller than revenue from brine. So if we can find the place to sell the brine, a portion of it, even 1/3 of it, we will be producing revenue much higher than water supply. And that is a very interesting observation because it changes the paradigm of desalination. For those you may have not been to Indonesia to see the first large-scale project, you know what happened with the desalinated water? It goes back to the sea and it's given away because the manufacturer is interested in the salt. And when I ask him, hey, this drinking water, why are you dumping it back? I have nothing. I mean, I make $60 million out of salt and less than $1 million out of water. I'm not going to bother with water. I just give it away. That is actually a very interesting and real example of where the industry is going. The most expensive source of water could become the cheapest source of water as long as we can cost-effectively remove minerals and sell them. So if we look at this, we can see at $40 a ton of production cost, which is actually the cost of production in Indonesia is $40 a ton. That's why I picked that number. So at $40 a ton, we have profit margin of 25 million per year of selling the sodium chloride. So it shows us that the profit margin is higher than the sales of water. It allows us a mechanism by which we can actually turn desalinated water to a main water supply source. Currently, only about 1.5 to 2% of the world's water is supplied by desalination. By tapping into brine mining, we actually can dramatically increase that amount as long as we have industrial development around us. Or even when you think about third world countries or global south, they can, even if they don't have immediate use, extracting those minerals can actually make them very attractive source of rare minerals and metals. This particular graph shows if we take 1,000 cubic meters a day of seawater, how much, and you see the cost of it, how much we are extracting from the various sources. As you notice, sodium chloride, and this is based on market costs in Saudi Arabia, but also in many other countries. Things like sodium hydroxide, magnesium, hydrochloric acid, those are all substances, chemicals that we could extract at very attractive pricing at present. The first large-scale plant that I mentioned was built in Indonesia in 2022. This actually presents the schematic of the facility. We have ultrafiltration for pretreatment, followed by nanofiltration to split the monovalent and bivalent ions. In this case, the client there, which is the food industry, is only interested in the monovalent, so that the bivalent basically is disposed of. So after we go through nanofiltration, seawater reverse osmosis separates the salt. At this point, the sodium chloride is the main salt in the brine. Afterwards, osmotically assisted RO is used to concentrate that salt to approximately 180 to 100,000. And then the concentrated salt is crystallized. What is interesting to underline here is this plant produces 0.2 million tons of sodium chloride per year, and crystallizer power demand is 5.3 megawatts per hour, and which is 50% of the total power demand. Why is that important? It is because it shows us one very important issue. The main cost and energy associated with brine mining is in the crystallization of the product. So if we could avoid crystallizing it, pumping it directly as liquid, or use alternative crystallization like membrane crystallization, we can actually make a very significant impact. As I mentioned, this project produces a brine at $40 a ton. If you use solely membrane technologies, that number goes to $18 a ton. Very competitive production cost. This basically shows the water treatment costs against various technologies. What is the important of this is the energy demand significantly increases as we try to concentrate more and more. That's why we have to start looking as an industry into a different way of concentrating and crystallizing. Concentration and crystallization are 2/3 of brine mining energy demand. This is an example of a plant that is currently being developed for the Jubail, city of Jubail in Saudi Arabia. And that's built in parallel with existing desalination plant. And that plant is 1 million cubic meters a day. And portion of the brine, a relatively small amount of it, is collected from the seawater RO system and then processed through membrane brine concentration followed by crystallization in this case thermal crystallizer, and then the two beneficial minerals produced are crystal salt and bromine. Why is bromine beneficial and where is it used? It is used in every well in the world that makes fuel oil. It is actually fire retardant. It is injected in the wells of every country that makes oil, and therefore has a huge market if you have that type of business around. Another facility, and that's the one in Dubai, Saudi Arabia, developed by NEOM, has a similar process to the one that you've seen, but it also focuses on, so we have ultrafiltration for pretreatment, seawater reverse osmosis, and then we ultra high pressure RO, but this one also has a slightly different component. Ultra high pressure RO, which the other facility didn't have. Ultra high pressure RO takes the brine from the conventional seawater RO system and concentrates it from about 68 to 70,000 to 120,000 TDS. And at the same time, ultra high pressure RO produces water. That allows us to increase the recovery of a conventional seawater desalination plant, which is about 43%, to all the way to 65%, and produce obviously much more water, and at the same time concentrate the brine. So starting from 120,000, the brine is then reconcentrated by osmotically assisted reverse osmosis, and then the concentrated brine, in the case of Dubai, gets split into two streams. One is actually thermal crystallizer, the other one is a membrane crystallizer. So we're running side by side the two technologies to see which one works better and what's the difference. That is very important because, as I mentioned, most of the energy in this type of facilities is energy for crystallization. So if we dramatically reduce this energy, we can dramatically reduce the cost. So when we look at this system, overall water recovery is 86%, so it's twice the 43% that we recovered. That's one advantage, we're producing more water. Second, salt recovery is 92%. All of those salts are actually of commercial value. Cost of water production is about 50 cents, and cost of sodium chloride production is about $35 per ton. This is with thermal desalination. As I mentioned, if we go with membrane crystallization, we would actually end up to $18 a ton, about a half. And that is because the energy demand for thermal crystallization is significantly higher. Just to give you a sense of kilowatt hours, the kilowatt hours per cubic meter of brine processed is approximately 75 to 80 kilowatt hours per cubic meter of processed brine, crystallized brine. In the case of membrane crystallization, that amount is 7.5. 75, 7.5. That is a dramatic decrease in energy demand. This is the plant, and it shows you in summary what are the key components of the plant. I already mentioned them. The membrane crystallizer, for the facility, you could see it at the bottom corner here. This component, it is fairly small and efficient. One very important component that really will change the world of brine mining is how we look at membranes. And that is when we tried to fund a project in Qatar, the investors were asking, okay, you have all these great minerals, and they're needed today, like magnesium and calcium and others. But what happens if nobody cares about magnesium 10 years from now? We know water will be needed 10 years from now, but what if the minerals that we're interested in today are great business proposition today, but 5 or 10 years from now, they're replaced by plastics, by other metal, as it was aluminum 10 years ago? And that's a very fair question. So it's very difficult to make brine mining on a large scale financially viable because of that reason, especially if you're producing many different minerals. And the solution to that is actually to develop membranes, which include special components inside them, ionophores, which actually can be selected for the particular mineral you would like to extract. So if tomorrow we want calcium or potassium or lithium, all we need to do is go to the seawater RO system, take the existing membranes, and put those that are selected for that particular mineral. That allows us to evolve as demand changes, as Also, the minerals that we are extracting change. We could use exactly the same seawater system and extract various minerals. We will have more opportunity for questions, so I don't have as much detail to discuss, but when you look at the plan of the future, you imagine multiple RO trains, some of them with membranes selected for lithium, others selected for potassium, others selected for magnesium. And I point out magnesium and magnesium selection because the membrane crystallizer that we use actually runs on draw solution of magnesium chloride. And we actually make our own magnesium chloride by directly extracting it from seawater. That allows us, when you bring the pH down of the water to about 4, all the magnesium switches to magnesium chloride, then through the selective membranes we remove it and recover it, and we use it as a draw solution for the membrane crystallizers. That actually closes the loop of cost-effective membrane crystallization, which otherwise usually the draw solution is the big challenge of how do you make that draw solution cost-effectively. In our case, we're making it of seawater. We're not buying it from outside. This is the membrane crystallizer. You can see the tiny crystals forming on the surface. This demonstration facility is for 40 kilograms per day. The total demand is 7.5 kilowatt hours, of which about 7 kilowatt hours goes for production and crystallization, and 5 goes for recovery of the brine solution. What's interesting about magnesium and why we picked it is if you look at temperature versus concentration, we only need few degrees change in temperature to double the concentration of magnesium chloride, and we're doing that through a cooling tower. So it's very easy and very low energy to concentrate magnesium chloride. That's why we picked it. This is the membrane crystallizer, 7 kilowatt hours for the crystallizer, 0.5 for the cooling tower, which is used to recover and reuse the draw solution. So compared to 80 to 85 kilowatt hours, that certainly breaks the energy barrier for desalination. I wanted to just say a few things about mineral products, and that is that the purity is very important for any of the products that we make, commercial products. The main problems that minerals create are magnesium, calcium, and potassium. They would have to be removed for the chlor-alkali process to be cost effective. And how do we do that? At this point, there are ways through dialysis and others, but now we're actually doing that through selective membranes. And if you ask me questions, I'll be able to answer in detail, but at this point we don't have the time. We also, as I mentioned, are generating plant chemicals from brine minerals, coagulant from magnesium hydroxide. Magnesium hydroxide is an excellent coagulant compared to ferric chloride. Anti-scalant from balancing of calcium and magnesium. If you ask me, I'll explain later because it's a little bit more complicated. Draw solution, magnesium chloride from seawater, as I mentioned that. Biselective seawater membranes, and calcium carbonate from the CO2 sequestration using nanobubbles, and that's where is Hamid, Texas A&M. He was here earlier. Yeah, so that idea came from him, and it's an excellent idea because it minimizes the cost of and efficiency of use of CO2. This is printing, 3D printing with brine, and as you can see, those are the shapes I mentioned that we use for coral reef habitat restoration. This already have been deployed. And then what is next? That's the main issue that we would like to understand and work towards, because you're the scientists that have to make it happen. First is multifunctional membranes. Seawater membranes for the last 50 years make only one thing, water. Now with brine mining, we are making membranes that can make more than one thing. They make still water, but also they would make a specific mineral. Currently, we've developed membranes for potassium chloride, lithium chloride, rubidium chloride, and magnesium chloride. That is possible by using different ionophores for every one of those substances. The same principle of production. NF membranes with magnesium rejection of 98%. We actually achieved that. Currently, we are achieving, using a company called Active Membranes, which you may have heard, we're pushing the envelope of 96% recovery in the NF system. Currently, recovery is at 75% with conventional membranes. So that's new. Brine membrane crystallization, forward osmosis to crystallize the brine to the level of commercial product. High pressure brine concentration, that is happening. There are new products that were just recently introduced. increase in desalinated recovery from 86 to 96%, thermally resistant brine membranes. One thing that you will see in the Middle East is very high temperatures of seawater. And as we pump and pump and pump to concentrate brine and crystallize it, we would end up at a point where we will hit the 40 degrees Celsius maximum, which will compact the membranes. So companies like Hypernautics, FTS, and now Dow are currently working on thermally resistant membranes where they operate up to 45 degrees Celsius and guarantee performance without compaction, or with typical minimal compaction. Post-treatment of seawater post-seawater RO NF membranes. One thing that you also will see in practice is every time you go and talk to real people about real projects, they say, don't touch my seawater RO system. You can take my brine, but don't put an F on the front of my seawater RO. So that basically caused the industry to develop a completely new set of nanofiltration membranes that are operating for splitting minerals on the back end, taking the brine, mixed brine as it comes from the seawater RO systems, and splitting it. The latest elements that we are developing currently actually also selectively remove sodium and potassium out of the product. So we create extremely high purity sodium chloride. The other thing is generating all desalination plant chemicals from brine. This is what we strive for, and it's possible. That by itself is certainly worthwhile for you as scientists to consider. There are opportunities to develop new technologies in for various chemicals, but it's all doable. Everything can be produced from brine. And that is a major breakthrough in terms of circularity and desalination. With that, I guess we have a 2-minute question and answer. And then at the end, we will have discussion at the end of the workshop for all questions you may have.
Just one burning question. Anybody just come to the mic and then you can ask now one question. Otherwise, we can, please.
Quick one. I don't know.
Yes, quick one. And then we will have a more discussion after three speakers' talks.
Yes, thank you for the presentation. Professor Nikolay from Kuwait University. I started working on the brine, you call it here brine recovery, we call it the brine management. I started with MIT for 7 years. I was the leader of the project, 5.5 million. The focus here about the power and the cost effective. We looked at both, also environmental impact. To us, environmental impact is very important, sustainability, because of the fauna and flora, the marine species, and also the brine is heavier than the ambient seawater and settles and causes
Unless mixed.
stratification and stuff like that. So in our projects, and we started very early, 2013, on the brine management. We did the treatment. We used ED, electrodialysis, pressure retarded osmosis to produce green energy from brine, ion concentration polarization. We got the patent with MIT. This is a treatment, and also disposal. We disposed it in a smart way to reduce this the density of the brine, and instead of settling, we just had it on the surface and then dispersed. So I do really support the cost effective, but also the environmental impact and sustainability extremely important for us to protect the coastal line is priceless.
Yeah.
Thank you.
Thank you. Yeah, I absolutely agree with you. That's really the reason why Saudi Arabia has invested a significant amount of research and funding in research, because they have a beautiful, pristine coral reef area along the Red Sea. And as we are looking at industrial development at this point and resorts, the main concern is, okay, now we're bringing a lot of people, we will have brine, water has to be produced and brine has to be generated. And we know from my experience here in Florida, we bleached our brine, our coral, and if you'd like to go and see real beautiful coral, which we do have here as well, you have to now go about 3 to 4 miles out you would see all the coral basically die. That's one thing we don't want to do in Saudi Arabia. And by this approach, we're combining environmental protection and at the same time beneficial reuse of brine. We call it brine valorization because we're basically turning brine into a commercial product. Thank you.
Thank you, Nikolay. Wonderful presentation. So next speaker is Professor